All right, last section, 6.7, end behavior and the graphs of polynomials. So what we're interested here is what happens, and this is kind of the basic idea before we get into the formal terms, but you have the x and y axis, and we're trying to figure out as a function moves in this direction, like as our x's are getting bigger and bigger and bigger, we want to know what's y doing. Is y going up or is the y value going down? So some functions as they move to the right, they start increasing. So if that was a scenario, I would say that, well, as x moves to the right, aka positive infinity, then the y values also are going to go up, which is considered positive infinity. And then we also want to know, well, what happens as our x values get smaller? Or as the graph moves to the left, what is the end behavior doing? And maybe it's a parabola, maybe it goes right back up. So that would be a scenario where, we would say, hey, as x goes to negative infinity, aka as x moves to the left, our y value goes up, or it goes to positive infinity. So up here would be positive, down here would be negative. Now, we can tell where it's going to go without using a graphing calculator based on the parent function. So when you look at this little table here, things with degree 1 typically are a straight line going up. A quadratic, if a is positive, it's going to be a bowl going up. If the number in front is negative, we know that it makes this come down. This over here would be some version of an x to the third power. But if I put a negative number in front, it actually is going to come down, go up, and then finish down. So all of these kind of get reflected or get bounced over depending on the number in front of the power. So these are x to the fourths, and these are x to the fifths. Now, something that you need to kind of understand from this picture, so I'm going to kind of go back and erase some of this stuff, is the big idea is the even powers. So you have 2s, 4s, we don't really go up to 6 on this chart, but all of your even powers, they're going to end up in the same direction. All right? The ends are basically either going to go, both up, or they're going to kind of both come down at some point. Now, if you're an odd power, if your power is like 3, 5, even 1 over here, all of those, you'll notice that the tails are on opposite directions. So all the odd powers, you're either going to have this side going up and then this side coming down, or it's going to start by increasing and then kind of go that way. Actually, I drew my arrow wrong there. Something like that. And as we do more examples, it'll kind of become a little bit more obvious. So let's move down, let's get into it. So end behavior is a description of what the values of the function, aka the y values, are doing as x approaches positive or negative infinity. And like I said, I moved to the right or to the left. So let's just look at a few examples. So if I put something up here like, y equals negative 5x to the third, and really whatever comes after that, it doesn't even matter. None of those other terms matter. It's this term in front, the leading term, tells you what's going to go on. So if I want to have an idea about the graph of this thing, I'm like, okay, I know x to the thirds, that's an even function. So this is, or an odd function, I mean. This is an odd function, so I'm going to be going in different directions. And the negative in front, this negative 5, that tells me that, I know normally x to the third does this. That's what the parent function for x to the third does. Well, that blue negative sign makes it come down and do the opposite. It's going to come down and do something like this. So when I describe the end behavior, how I write that or how I express that in symbols is I say, well, as x goes in the positive infinity direction or to the right, our y values are decreasing. They're going to approach negative infinity. And as x moves to the left, or as x goes to negative infinity, our y values are getting bigger and bigger. They're going up. So y is actually approaching positive infinity. So this is how you write end behavior with the correct notation. So let's try another one. Come over here. We'll do, y equals 2x to the 6th plus, who cares? This doesn't even matter. All the rest of the terms don't matter. And so if I'm looking at this one, I'm like, all right, x to the 6th, it's kind of like x squared, but there's some extra squiggles in there. And I know that y equals x squared goes up. And since this number in front is positive, I know it's still going to look kind of like x squared. So it's going to come down, and it might have a couple little weird squiggles, and then it's going to go right back up. So on something like this, I would say, well, as x moves to the right, or as x goes over here to positive infinity, well, y is also going to go to positive infinity, which is up in this direction. So y's are getting bigger as x's are getting bigger. And same thing, as y goes to negative infinity, aka over here, well, my y's are still going to positive infinity. So sometimes these two should be matching up and they should be the same on all of your even powers. Your y's are going to be the same in all your even powers. They're going to be different on the odd powers. That's kind of the big idea that you need to figure out. But you have to know what the parent function looks like to understand, what's going on. So let's look at some down here. Identify the lead coefficient, the degree, and the end behavior. So first of all, I got to look through the terms and see who's the biggest. Luckily, this one is written in descending order. It goes 3, 2, 1, 0. So this is the leading term in the front. None of this even matters. We don't care. It doesn't tell me anything about end behavior. So what I need to answer, well, who's the leading coefficient? So the lead coefficient is a -4. So that tells me my parent function is going to be flipped. It's going to be inverted. My degree is 3. So this is a third power. So I got to understand, well, the parent function for x to the third looks like this. All right, so this 3 kind of gives me an idea of what the parent function looks like. But this -4, that reflects it. So I'm actually doing that. So the parent function gives me an idea that they're going in different directions, but then I have to know that it kind of flips. So what I'm going to say here, as x goes to the right, positive infinity, y is going to go to negative infinity. As x goes to the left, y goes up, positive infinity direction. All right, moving a little quicker, this next one, the degree is 6. So I know the parent function for y to the 6th is, it's kind of like y squared, but it may have a couple extra squiggles in there. But they're both going up, and my lead coefficient, my LC, is just 1. So it didn't get flipped. So basically, as x moves to the right, y goes up, and as x moves to the left, y also goes up. The end behavior is the same on both sides. All right, 3 and 4 is just kind of a matching. It says, hey, identify whether you're even or odd degree, positive or negative. So looking at these graphs, well, I know because the ends, this side's going down, this side's going up. This is going to have an odd degree. Now, I kind of know later on that it's going to be more than x to the third because it's got some turning points. We'll learn about that here in a second. But it's got an odd degree because it's going in different directions. And x to the third looks like this. And this one has that same end behavior. So it must have a positive lead coefficient. Positive lead number in the front. Well, these guys are going in the same direction. So this is an even degree. And it also has to have a positive because x squared does like that when the lead coefficient's positive. Kind of goes back to your quadratic stuff. Now, a turning point is where a graph changes from increasing to decreasing or vice versa. This point corresponds to a local top or a local bottom, aka a max or a min. So then we have this kind of rule here that says a polynomial function of degree n always has at most one less than that turning points, and at most that many x-intercepts. So let's take an example of, I'm going to do kind of an extreme example. Let's take an example of something in x to the 5th power. All right, so example in x to the 5th power. Now, an x to the 5th power may look like this. It's kind of like x to the 3rd, up, down, up, down, up. All right, that would be an x to the 5th. It's got a couple of extra squiggles there. Well, these turning points are where the graph changes from increasing to decreasing. So we're going up, 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 and right here we start coming, so we're going up, 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 up. We get to that turn point, and now we're going down, 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 boom. We get to another turn point. So maybe the turn points I'll make green. And then we start increasing. We're going up, we're going up, we're going up, we're going up. Right there, turning point. Now we're coming down, coming down, coming down, coming down. Right there, turning point. And now we're going up, 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 up. So if we looked here, our degree, our n in this case was 5. It was a degree 5, but we had 4 turning points. We had 1, 2, 3, 4 spots where we changed direction. So we had at most, it could never have more than 4. Now, it might have less than 4. All right, it may not have those squiggles in there, and it might just kind of bend instead of actually change direction, but at most. Also, we're going to have at most n x-intercepts. On this graph, I actually have 1, 2, 3, 4, 5. I have all 5 of them. Now, I could have changed this a little bit, and maybe this thing comes up, and then it comes down, and it goes up, and maybe down and then up. So if you notice this one, it only has 3 of those x-intercepts. So just because you're next to the 5th doesn't mean you have to have 5, because you may have some of those complex roots, some of those imaginary stuff where it doesn't cross the x-axis there, but there's actually more roots. All right. Use the calc function on the graphing calculator to estimate the local max, local min. So I'm going to show you really quick how to graph these. So I'm going to take this out, open up the graphing calculator, fire it up, and I have f of x equals 2x to the 3rd power and minus 12x and plus 6. And I'm going to go to my window and just see, whoa, yeah, see my y max was something crazy. So I'm going to just go zoom standard, zoom 6, and graph this thing. Now it looks to me like I'm missing something. It looks like I'm missing something right up here, and it's off my screen. So I'm not going to zoom out. I'm just going to make my y max go a little bit bigger. So let's go to our window. Let's make our y max go a little bigger. Maybe go to 20. Regraph it. All right, now I got a nice little top. So if I want to figure out, I'm trying to figure out, where is exactly this point right here? Like, what's that ordered pair at the top? I can use the calc function. So what I'm going to do is I'm going to go second, trace, and there's a maximum there. So I'm going to hit 5. And now I got to do the left and the right bound. So I got to go on the left side of that hump anywhere on the left side, hit enter. I'm going to go over to the right side of the hump, hit enter, and then it says guess, and I say, yeah, guess. So there it goes. It tells me that for my x value, I have negative, let's just call it 1.4. And then for my y value, so this is our local max, the nearby max. And then the y value, it's at 17.3. So that's our local top. Well, now let's go get our local bottom. So I'm going to kind of move the cursor down, and I'm going to go back to second, trace. Now we have a minimum, so I'm going to go to 3. And let's kind of go down a little closer. So enter on the left bound, trap the right bound, enter, guess, and it finds the lowest point in between those two x's, which our local min is going to be negative or positive 1.4, negative 5.3. So that's our local minimum there. All right, got another example. We got example 6 here. Let's give this one a shot. Clear that out. Go back to y equals. Clear. We have x to the 4th power plus 4x squared minus 6. And let's see if we get lucky with the window we had. Not too bad. Now I don't see, I was hoping maybe I would get a couple of squiggles in there. I was thinking, so here's kind of what I was thinking in my mind. I was thinking that an x to the 4th may do something like that. And I would have a local min, a local max, and a second local min. 3 turning points. But right now it's not very clear. So I'm going to kind of zoom in. I want to see what's going on a little, I want to see what's going on a little bit closer. Let me try to pull back up my calculator. Somehow I lost him. I want to zoom in right, doggone it. I want to figure out what's going on right in this area. So I'm thinking between like -2 to 2 on my x's. And then my y's maybe, I don't know, -3 to -7. Like I'm going to try to zoom in. -2 to 2, -3, -7. So -2 to 2. And then -3 to -7. Let's just see if domain range, what I do. Quit. Oh, y min has to be the -7. So if you ever get that error message, it's probably because your min is bigger than your max. There we go. Yeah, I'm not seeing any squiggles, so this one may just have one local min. All right, it might just have a local min, and let's just see if we can calculate it. Second, calculate. Number 3, left bound, right bound, guess. So right there, and if I wanted to, I could actually go to the table and kind of investigate, but it looks like this one just has one local min, even though it's an x to the 4th. We only had the one turning point. So that's kind of good that that example came up. So we have a local min at 1.6, comma, -6. All right, let's see what we got here at the bottom. Get rid of him. Story problem. So this looks like one of those problems. We've done quite a few of these where you have an open box by a sheet of metal. So we have a sheet of metal, and it's 24.5 feet by 18.5 feet. We're going to cut some corners out so that this box can fold up. So we're going to chop off these pieces. And, you know, its dimensions are x by x, so we're not really sure how much they're going to cut. So find the maximum volume. So I think we're going to graph this problem, and we're going to see a maximum somewhere. So let's try to come up with a volume equation. Volume is going to be length times width times height. So if we have this kind of 3D box, it's going to look something like that. And my length, my dimensions here in the front, well, that is going to be 24.5 minus those two x's that I cut out. So I have a 24.5 minus 2x. Well, then over here on the width, this piece, that's going to be 18.5 minus 2x's. And then the height is going to be whatever I fold it up as. That's just going to be my x. So when I write all this out, the volume is going to be 24.5 minus 2x, 18.5 minus 2x times x. Now, I could multiply all that out to get it in standard form, but I don't need to do that. I'm just going to graph this. I'm going to just graph it as is, and I'm going to look for a maximum. And that maximum, remember, the y value is the volume. So when I look at this graph and I get this ordered pair, what these two numbers are going to represent, the x represents how much I'm going to cut, the inches that are cut off on the square, and then the y value is actually what the volume is. So let's punch this into the graphing calculator. Bring it back up one last time. So let's graph this thing out. And maybe guess I don't really need that stuff on there anymore. So I'm going to go y equals, get rid of u, parenthesis, 24.5 minus 2x, parenthesis, and then parenthesis, 18.5 minus 2x, parenthesis, and then times x. And let's just graph it. Oh, my window's pretty crazy. So let's just, before we get all happy zooming out like some of you guys do, sometimes it works, sometimes it doesn't. Let's think about, go back to our box. You know, if this was 24.5 and this is 18.5, let's think about what are the possibilities for x. You know, like honestly, if x equaled 9, you're going to be cutting 9 inches off of each side. You'd be cutting off 9 over here, 9 over here. You'd only have half an inch for a box. So it's not going to be bigger than 9. And it can't be negative. So I think my x's are trapped between 0 and 9. The box itself, I don't really know. Like, that's going to be pretty big. You know I could multiply possibly this number times this number times the height, but I don't really know the height right now. So let's just kind of start off with a number around 200 or 300, see where we're at. So let's go over here to my window. I'm going to control x min from 0 to 9. And I'm going to make the y's go from maybe 0 to a couple hundred. And I don't know, let's count by 50s. Graph it. Well, I'm missing a lot. I got to go way higher. So on my window, I'm going to go bigger. I'm going to go to like 500. Graph. Ooh, 500 is not high enough. So let's go to 1,000. Why not? There we go. So now we kind of see what's going on there. And those are my only possible x values. So let's find that. Let's calculate that max. Second calc maximums number 4. Got to get to the left side of the max. Enter. Get to the right side of the max. Enter. Guess. Yes. So it looks like, if I really wanted to be perfect on this thing, it looks like x, the amount I cut, I need to cut 3.48 inches. And if I cut 3.48 inches, when I plug it into that volume formula, it looks like my volume, or my y value, is going to be 704.4 cubic inches. So that right there is going to it's going to hold the most stuff if I use that type of cut, given that certain dimension of sheet metal. All right, hopefully this helps you out, get you ready for the practice. See you.